languages. And let me first say really quickly what I mean by safe language. And the easiest way to do that is to exhibit an unsafe language like C, which I'll pick on in the talk, and a program that exploits C's unsafe features, pick a random integer, use the cast feature to say, oh, this isn't actually an integer, it's a pointer to an integer, and whatever's contained at that pointer, add 1 to it. And, well, what does this code do? This depends on where this code's executing. If you've got a program in user mode, maybe you'll be lucky and this will touch memory that's not mapped and you'll get a protection fault. If you're running in the kernel, well, it could overwrite the page tables. It could overwrite interrupt tables. It could even trigger action by a device that's listening to memory-mapped I/O addresses. In other words, an unsafe program, by incrementing an integer, can perform actions that really have nothing to do at all with integer arithmetic. So in a safe language, when you add 1 to an integer, that really means add 1 to an integer and not take some nearly random action on a completely different type of resource. And a hardcore C programmer might look at this and say, well, this is obviously silly code. I would never write code this silly. So I would argue that safety does matter in practice, and maybe one of the best examples is a simple buffer overflow attack where you have some stack space. On that stack lives a return address and some space for an incoming network packet, and you read in the network packet, and maybe it's just a little longer than you anticipated, and it overwrites the return address. And when the function tries to return, it jumps to an arbitrary location containing malicious code inside the network packets. In a safe language, this particular attack is impossible because, if nothing else, data inside a network packet has a different type from a return address. And in a safe language, you can't confuse values of different types. So you can't try to use bytes from a network packet as a return address. So I got interested in safe languages working on extensible systems in the J-kernel project and the Luna project, where we were trying to build a system that you could download untrusted code into a process and run this code along with other untrusted code all inside the same address space without the danger of the untrusted code overwriting any of your runtime system, interacting with your operating system. And we relied on type checking both in the compiler and dynamic type checking to make sure that this code, which happened to be written in Java, didn't do anything bad to the runtime system, to the garbage collector, to other bits of code. So a lot of people have worked on this idea, and there's still a lot of issues to making sure that this whole system is really secure. In particular, well, what if there's a bug in your type checker and it actually lets unsafe code slip through? Or what if there's a bug in the allocation and garbage collection that allows the untrusted code to dereference a dangling pointer? Or what if there's bugs in other parts of your runtime system? Maybe there's a race condition in here that the untrusted code can exploit. So some people have proposed, well, rather than having this code here in a safe language and this stuff written in C, what if we try to write all of these things in the type-safe language so that we won't have to trust the programming of the allocator, the garbage collector, and the rest of the runtime system quite as much. And in fact, you may be able to take large chunks of this, maybe even all of the allocation and garbage collection, and apply all of the same type checks that you do to the untrusted code to make sure that the untrusted code can't exploit, say, the garbage collector in order to try to harm other code or to try to harm your operating system. So, all right. Suppose we want to, say, rewrite the garbage collector in C# or Java. How well are we going to do? The goal of a garbage collector is to go through your heap, find objects that can no longer be accessed, and deallocate them. You're immediately going to run into the following problem. In almost every safe language there is, you can't deallocate an object directly. And the reason is you might end up with a dangling pointer. If I say free the pointer P1, and there are also other pointers P2 and P3 to this object, once I free P1, I have P2 and P3 pointing to the empty space where P1 used to live. And loads and stores through P2 and P3 are now unsafe. There may be different types of data allocated where that object used to be. So here's what I want to try to do in this talk. On one side of the spectrum, I've drawn C pointers, which are very powerful but unsafe. You can perform casts on them in pointer arithmetic and get yourself into trouble really fast. On the other side, I've shown typical types that are provided by languages like Java and C#, where you only have a certain number of predefined safe operations that you can perform. So for example, you may be able to get a field out of an object after performing a null pointer check. Or you can set an array element of an array after performing a null pointer check and a bounds check. But you can't free an object directly. You can't perform pointer arithmetic safely. The central question of this talk, is there a middle ground here where we can get most of the power of C pointers but still be safe, like Java and C# pointers? I'm very happy to throw that into. Yeah, actually, the dotted line was just supposed to indicate the user mode part of a process. But given that the OS kernel is just as susceptible to bugs like buffer overruns and race conditions that user mode code is, I'd be happy to do anything I can to improve the reliability of this.
How much of the untrustability of the garbage collector do you think is attributable to the fact that obviously, even if it's written in a safe language, you can't defend against all possible coercion.
Right. You can write a trivial safe program that says, if they pass me a certain special magic argument, delete all the files that I know about.
Or more to the point, I think you want some separation between code. You might be able to tie up the garbage collector so it's not responsible to anybody else.
Right.
Otherwise, you use it over and over. All these different types. So do you think that it's a really big, important way to ultimately write those complaints?
Maybe one way I can answer that question, and I should repeat the question, is there a big win here from moving from unsafe code to safe code? Maybe one way I can answer that question is to cite a search study that looked at vulnerabilities and how often what kind of different vulnerabilities were being exploited. I think they found something like 50% of vulnerabilities that were being exploited were buffer overruns. Yeah, you can fix buffer overrun vulnerabilities, or almost all of them, in an unsafe language, just by using some simple techniques to protect the stack. But I still think, based on that, and based on, general experience, some of our own experience with writing software in very strongly typed code, we've seen that once we have type checked the code, we've actually had very few bugs in the software. And I think, hopefully, very few bugs will translate as fewer security vulnerabilities. Any other questions before I go on? So let me kind of give an outline of the talk from this point on. Um, the main goal of this talk is to develop safe mechanisms for accessing low-level resources like memory, and also devices that can replace unsafe mechanisms like C and C++ as pointers. I'll do this by adding capabilities to the operations that we can perform on low-level resources, so that when you access a low-level resource, you have to provide a capability that says that the access is actually safe, and that capability will be checked at compile time. I'll start out by treating capabilities as ordinary data, which unfortunately is called nonlinear data. And nonlinear data just means normal data that you can copy around, pass to functions, put in data structures. Later on in the talk, I'll talk about restricting the ways that you can use these capabilities. And I'll do this by claiming that the capabilities are linear, which will mean that you don't have as much freedom to pass capabilities around and put them in data structures. If I give you a capability, I lose the capability when you gain it. The only way I can get it back is if you give it back to me and you lose it when I gain it. So by restricting the operation, by restricting the way that we can pass around these capabilities, we'll be able to increase the power of the operations that the capabilities can check. And I'll wrap up the talk by briefly describing how we use these types to implement a garbage collector completely in a type-safe language without relying on any unsafe features. Okay, so let me introduce the nonlinear memory types here by comparing them with ordinary C pointer types. And I've shown up here some diagrams of operations on pointers. So taking a C pointer to a type T, you can load a value from the memory that that pointer points to, or you can store a value of type T in that address. Or you can crash the computer by using the appropriate casts, or maybe dereferencing a dangling pointer. What I want to do is to take these operations and implement them in a way that doesn't allow us to crash. So here's how I'll go about doing it. In order to load a value, you have to present two things now. One is the address of the value that you want to load from, and I'll write the type of that address as int I. And this just means the one integer that is equal to I. So a type int 7 just contains the one value 7. 7 has type int 7, but 8 does not. This is called a singleton type. And it's useful to connect the type specified in a singleton type with the capability here. When I do a load, I have to provide an address, and I have to provide a capability that says, at address I, there lives a type T. If I provide those two things, then I'll get this value T out. And the same thing for a store operation. If I provide the address I, a capability, and nmem stands for nonlinear memory, that says I has type T, I can store a value of type T in here. All right, now it may not be obvious at the moment why I'm splitting a pointer into these two different pieces here. And I'll define a pointer to just be the capability together with an address here. So I'll go through several examples implementing simple pointers to single words, implementing pointers to objects, null pointers, pointers to arrays, and so on, using these basic primitives. And I'll put the examples in a language called Clay, which I developed along with some students at Dartmouth College. And it's supposed to kind of look like C, sort of, except with a very advanced type system with lots of polymorphism and lots of static checks here. So this is a Boolean pointer defined to point to a Boolean in word address 7 of memory. and only word address 7 of memory. So the two parts say that at address 7, there lives a Boolean, and oh, by the way, here's the byte address that you'll need to use for loads and stores to get the Boolean out of memory or put a Boolean into memory. For better or worse, our capabilities use word addresses instead of byte addresses, but the x86 architecture that we built this on requires byte addresses for loads and stores, where every word has 4 bytes in it. So we end up having to multiply this by 4 so that we have the byte address corresponding to word address 7 as our address field there. Now this is kind of a silly example because it's only a pointer for address 7. Let me generalize this by using polymorphism here, and I'll say the pointer is polymorphic over all integers I. Whatever I is, if we have a Boolean pointer for I, we know that in word address I there lives a Boolean. And in order to use loads and stores on this, we have the byte address 4 times I. So I'll show you some code that uses a pointer. So if I have a Boolean pointer, say that I happen to know points to word address 7, I can pass this on to another function, g, which is a little more general. And this function is polymorphic over all integers I1 and I2. It says for any I1, take a Boolean pointer P1, a Boolean pointer P2, and use the integer address and the memory capability to load a Boolean value from P1. Do the same for loading a value from P2. Yes?
Rather than constructing a local, you can't use the whole plot like constructing local because it doesn't match with the.
Yes. So I guess one way to paraphrase the question is, where do you get these capabilities from in the first place?
Yeah.
So this is a difficult question for nonlinear capabilities. One answer would be, okay, we could build an allocator, and you just say, I would like an integer. Here's the initial value of the integer. Find some place for it in memory, and give me the capability for it. And that would work fine for allocation. It would be a real problem for deallocation. And this is why later on in the talk I'm going to move from nonlinear data to linear data. And what we'll actually see is that when the program starts, it's handed the entire address space's worth of linear capabilities, filled with zeros, say. And then it can build its own allocator out of those. Yes?
So a lot of this technique is pretty much into
Yes. In fact, let's answer that question. Let me explain what happens when we type check and generate the code for this.
So if I have a value of type 4 what are the actual values within all of it? Like what is the value of type 4?
So if I take this bool pointer 7 here, a value of address is just a value that has type 4 times 7 is actually just that constant, a normal integer constant. I can assign it to that field. The capability, I cannot make those up myself. I have to get them from somewhere. I have to have been given them from some trusted resource. I can't just forge a capability whenever I feel like it. Okay. The runtime representation is this big, 0 bits long. What our type checker does is first to go through the program with all of these elaborate type annotations here and check things like, when you do this load here, the address better match the capability. If I said p1.address and p2.mem, the type checker would complain because it would say, oh, you know, I don't know that I1 and I2 are the same. The capability might not match the address. Once the type checker is through, we erase the capabilities. So this field disappears. We're left with just one word, which is the address. We take that stripped code and hand it to a C compiler, and that generates our code for us. So if you look at the C code that this turns into, it's basically the same sort of thing that you would write in C directly. Pass a one-word pointer as P1, a one-word pointer as P2, perform a couple loads, and then do something arbitrary with the data that you loaded from memory. So what we're trying to do here is to do as many checks as we can at compile time and not add any additional space overhead and as little additional time overhead as possible. Any other questions about this? Okay. Whoops. All right. If you have a Boolean pointer, this says for a Boolean pointer for a given I, there's definitely guaranteed to be a Boolean at address I. But sometimes this is too strong of a statement. Maybe you want a pointer that could be null and possibly points to some memory location with a Boolean, but is possibly just a null value. Rather than add that as a primitive to our type system, we just implement it as a derived data type. And here's how we do it. We say a nullable Boolean pointer is a pair of two things, an address I, and if I is not equal to 0, it's a capability that says you can go to I and find a Boolean. If it is 0, well, we've got nothing here. We don't have any capability telling us about memory location 0. So I can use this in code like this. If somebody gives me a potentially null Boolean pointer, I first have to test it to see, hey, is the address here, which is supposed to be 4 times I, equal to 0? If it is, I can't dereference the pointer. So I'll just return some dummy value false. Otherwise, the type checker is going to know in this branch of the if-else statement, in the else case, 4 times I was not equal to 0. And therefore, I is not equal to 0. And therefore, this coercion here that says, go into this if type and pull out the memory capability, this is legal because here in this else branch, we know I is not equal to 0. Excuse me? What we do about that, okay, let me, so one question is what do we do about integer overflow, integers that are bigger than 2 to the 30 or 2 to the 32 and so on. And let me take one big step back and talk about how the type checker handles this in general. We didn't make up this idea of using these singleton integers and having the type checker track known integer constraints through if-else conditions. This is actually developed at Carnegie Mellon by Frank Fenning and Hongwei Tse. We just adapted it to a C-like language and implemented it in a complete way. And the tool that we used was from the University of Maryland called the Omega test. It solves systems of arithmetic constraints, where each constraint can talk about variables, can talk about inequalities, less than, greater than, equals, addition, subtraction, and multiplication by constants. Those form a decidable system which, in small cases at least, can be efficiently decided. And we changed the Omega test so that it worked on arbitrary precision integers. So every time you see an int I here, this is an I ranging from -infinity to +infinity. Now we don't assume that the arithmetic performed by equals, equals, plus, and other C operators is arbitrary precision. For those, we assume that it's mod 2 to the 32. And in order to make the checking tractable, most of the basic operators in C, we have conditions saying, OK, you can add x to y. But if you want any static type information about the result of that addition, such as it being less than 0 or greater than 0, you have to know that x and y aren't large enough that their sum might overflow. So this means sometimes we'll have to add in conditions to the functions saying that the data we're dealing with is smaller than a certain range, so it won't overflow. All right, there's one null value. How about 2? Maybe you might want a left null value and a right null value. Well, you can implement that too. You just say, we have a memory capability if I is not 0 and if I is also not 1. And if you try to run this original code here with this new type, the type checker will complain at you. It'll say that in the else branch here, well, it's true that we know from this test that 4 times I is not equal to 0, but maybe 4 times I is equal to 4, and I is equal to 1. And if I is equal to 1, this condition here might not hold. So this code, as it stands, would be a type error when you tried to extract the memory capability from inside this if type.
What's the type of mem if the condition doesn't hold? Just untyped string?
Right. There's nothing that you can do with this type that's interesting if you don't know that this condition is true. If you know it's true, you can apply this coercion here. Otherwise, you have it, but you can't do anything with it. And we do have versions that have both an if and an else part. So I can fix this code here by extending my check to make sure that the address is not 0 and it's also not 4. If it is 0 or 4, we go to the if case. Otherwise, we go to the else case. Yes. And the structure of the type system where we've factored most of the arithmetic types into the types themselves, and we talk about constraints as being on these type variables rather than being on ordinary variables like p. This actually makes the type checking quite easy. It means that we don't have to do general dependent type checking, which is very hard. Okay, so here's another example. Instead of just a pointer to a single Boolean, how about a pointer to a pair of Booleans? And for this, I'm going to use a single address to refer to both of the Booleans. In this example, I would just say, okay, our address is word address 7. At 7, there's a Boolean, and at 7 plus 1, there's another Boolean. And I can write a function here that uses the first capability, mem1, to load directly from the address, and the second capability to load at that word address plus 1, or the byte address plus 4, and get 2 Booleans out of memory that way. So why stop at 2? Why not have a whole array of Booleans, or a whole array of any type t, actually? Here's a much more abstract-looking type that defines arrays of any element type t that we want, going from address I up through address k minus 1. So an array of start I, end k, element type t is defined as, well, if I is equal to k, this is an empty array. There's no data in it. There's no capabilities. We have nothing at all. If I is not equal to k, we'll have one capability at I, plus recursively, maybe some more capabilities starting at I plus 1 going up through k. So this is a recursive type definition here, kind of like the way you would define linked lists, except instead of defining elements that are laid out non-contiguously in memory, we're defining addresses one after the other, starting at I going up through k minus 1. Yes?
So I guess I think the way to define a way saying, okay, if I is equal to 0 and k minus 1 has the
Yes.
Symbols or what you know, using these things
The right, right. The way you would get uh, a value that said, well, you'd have to say something like, for all j, if j falls between I and k, we have a capability that tells us that element j has type t. So you'd have to write a function that's polymorphic over all j. When you write that function has to have a body that knows how to go out and find the right capability. So for example, you could write a function that is created by having maybe 5 capabilities, and it has an if-else inside the body of the function that says, oh, if we're looking at the first one, return this capability. If we're looking at the second one, return this capability, and so on. But ultimately, you're going to need some sort of data representation that you can use to find capabilities in an arbitrarily long array whose length is not known at compile time. Even if ultimately the type you give it is the type that you said, polymorphic over all j between I and k, you have to treat these capabilities as data and put them somewhere where you can find them. Actually, not yet, because I do have a function that actually does exactly what we were talking about, unwinding this data, going through it to find the right capability. And this is a key function here. It's going to say, for any j in the range I going up to k, take an array going from I to k, and return just a single capability, the capability for j, from this array. And it's going to do this by simple recursive function definition. If I is equal to j, we've found the element we're looking for. It's the very first element in the array. So we just go and get the mem field from this. Otherwise, we recurse on the next element of the array. Yes? It's never executed. So this is kind of a strange thing from a programming perspective, to write a function that deliberately will never be run. But this is actually what logicians do all the time. They write proofs, and they say, all right, if you fed particular arguments to this proof, it would prove a particular case of this theorem. And it's guaranteed to do that because we can type check the proof. So you don't actually have to ever run it because it's guaranteed to work if you did. A way to look at this from a programming perspective is to say, well, this function's silly. It takes no data at runtime. This array consists entirely of capabilities and no real data. It returns nothing at runtime. It does nothing at runtime inside the body of the function other than calling itself. And a final condition is it's guaranteed to terminate. And actually, there's a little annotation that says, in k minus I recursions, this thing will terminate, and this has to be checked. If all those conditions are satisfied, there's no reason to call this function at runtime. If we did call it, well, it would actually recurse and return this element just like we thought it would. Yes? Because of the yes.
Just the first half, the obvious conclusion applies. Vectors starting at I and
Oh, so first of all, remember these integers range from negative infinity to positive infinity.
that's what I said.
So
But just for the first step, ignoring the checking cycle.
right, if we didn't have any sort of guarantee that I was less than K, this wouldn't be good enough for the type checker, and it would complain that we don't necessarily know this terminates.
You can't access when you're using just these things this thing here for recursive looping.
You could actually write just an ordinary function that goes through and picks out fields out of this.
Yeah, except that you can't. That depends upon the value of the allocated to each cell.
Well, it's more than just being sane. It's actually impossible to generate something of type array ranging from 5 down to 3. There just is no value that has that type, and there's no way to construct a value of that type. Okay, so what we've got here is less of a program function and more of a proof that says if you know you have an array of t elements going from I to k, that proves that element j residing in the bounds of the array has type t. So we've kind of built up our own little coercions that we can use here. And by doing so, extended the power of the type system. Okay. Any other questions about this? Yes. At these addresses. So the data is actually in memory at these addresses. There's no data at all in this data structure called array. The only thing in the data structure called array is capabilities telling you that in memory at these locations, they're actually. Right. Yes, exactly. And an address. Put them together, and you've got something that you can actually use. Right, as in this example. So if I have an address that has type int7, and I have an array going from 5 up to 9 full of floats, I can use this coercion here to get out a single capability for address 7 having type float, and then put that together with the actual address and a float value and do a store to memory. And the type checker will make sure that 7 is actually between 5 and 9. If I didn't know at compile time that the element I was looking for was in bounds, I'd have to do a runtime check, the same way I did with the null pointer. Yes? This is way too fast, I think. Oh, it's strictly a capability used for the type checker. Yes, for element I. And then by this recursive definition for I plus 1, I plus 2, I plus 3, and so on. So when we go through all of this work here in the type checking, all of this boils down to take a float, store it at address 7. That's what the actual C code that's generated by this example does. Okay. So any more questions about this? This is going to be as hard as it gets. Almost. So let me take another resource here. Rather than memory, we might also talk about devices. And so here's a really old network card that we were using in our group, a 3COM 3C509 Ethernet card. And if I go to the documentation for this, this says that if I access port 0 and do a read on it, I can read data from the read queue. And so I'll give myself a capability to do that with. If I have a capability that claims that at a particular base I/O address in I/O memory, there lives this particular Ethernet card then I can pass in the integer address of an I/O operation and do a read operation and get a byte from the receive queue, from the card's receive queue. This picture is a little too simple. You might imagine that an Ethernet card is more complicated than this, and it is. So I'd just like to bring up two questions that are unanswered by this. How do we even know that there's a packet sitting in the receive queue of the card to read data from? If you read the documentation, it says that an operation to read data from an empty queue is undefined, and a safe language shouldn't allow you to make undefined operations on your hardware resources. And also, there's more than one register window in the card that you can configure it with here. I have to configure the card to be in register window 1 in order to do this data read here. If it's configured to be in a different window, it might do something completely different. In register window 0, instead of reading data from a packet, it would read the manufacturer ID, which is not what we want. So there has to be some more to the story here. This picture I've got up here is not enough to capture using a device safely. All right, so what I'm going to do is move from nonlinear types to linear types. And the key difference between linear types and nonlinear types is that nonlinear types allow aliasing. I can have 3 different pointers to the same object. And as I said before, this can leave you with dangling pointers. If you have alias pointers pointing to where P1 used to live. So there's a simple solution to this. Let's ban aliasing. Instead of having this picture over here with these doubly linked lists and this directed acyclic graph, let's have a nice, beautiful, clean world full of trees. Because that's the only data structure we get in a linear language. And the operations that I do on these data structures ensure that there's always exactly one pointer to each piece of data here. So for example, if I read this pointer into a variable z, my type checker says, OK, z points to an object, but the type checker disavows all knowledge of what this field, which used to contain the pointer, has. So we don't know that there's a pointer from there to here. The only pointer we know about is this one single pointer from z to this object. If I transfer this pointer from x and store it in that location there, I lose the value from x. And the type checker now says x is unassigned. If I try to access it, it'll be a type error. It'll complain x doesn't hold anything. So I can move linear resources around, but I can never copy them. I can never duplicate them. I can never discard them. And as long as I'm happy with trees, that's OK. I'll talk a little bit about how to get aliasing back into the picture later on here. But let me just move with this for the moment. So let me replace nonlinear memory capabilities with linear ones. Now, a linear resource is something that if I give it to you, I lose it. And if I want it back, you have to give it back to me, and then you lose it. So if I give a linear memory capability to a load operation, I lose it, and I have to get it back by having the load operation return the capability again to me. Now, this brings up a really interesting opportunity here for the store operation. In the nonlinear case, if our capability says location I has type T, we can only store values of type T to that. Because, say, memory location 10 has a float, I can't go in there and just say change it to an int, because there may be other copies of this capability floating around in other parts of the program that still think it has the old type float. And I don't want to allow 2 different inconsistent views of the same memory location to arise, because then I could confuse pointers. I could confuse different types and crash the system. But in the linear case, when we perform a store, we give it the one and only copy of the capability for memory location I. Since that's the only copy, and we've just consumed it, in the store operation, we can generate a new capability that has a different type T prime. And we get to pick T prime to be whatever we want. So I can change the types of memory locations by using these linear memory capabilities. So here's a quick example of something you can do with linear memory capabilities. If I start out with 3 having type float and 4 having type int, I can load the float from memory location 3, store it into memory location 4, load the int from memory location 4, store it into 3, and just swap the 2 values. And I end up with capabilities saying that now 3 has type int and 4 has type float. The int and float are swapped. Oh, okay. I think it's exactly what you said in the second part, which is that load has this type. The actual implementation of load is just an ordinary load you'd find in assembly language or C. There's no extra runtime overhead associated with tracking these capabilities. It's purely a static type checking mechanism. Okay, so one more example. I can go back to this device example and fix a few things up here. So let me extend this capability to be linear. And by the way, for the rest of the talk, I'm going to make sure that all my linear resources are colored lime green, and all my nonlinear resources are colored navy blue. It's kind of hard to find colors that begin with L and N. But this Ethernet capability is now a linear capability that, in addition to specifying the base I/O address of the device, specifies which register window it's in, how much free space there is in the transmit queue, and how much space is full in the receive queue. And in order to call the read byte operation, I have to make sure I'm in the proper register window, which happened to be 1 according to the documentation, and that there's at least 1 byte available to read. This capability will be consumed by the read byte. I'll get back a new capability saying that everything's the same, but now there's 1 less byte available to read. So if I start out with a linear capability saying there's 100 bytes available, I can call this 100 times, but no more. Yes? They are integers at the type level. They're integer types. One analogy would be in C++, you can use integers as template parameters and template arguments. It's part of the capabilities type, yes. Right, you couldn't just say, right, I think it's in register window 5. Right. So here's another operation. You can set the register window, and I won't bother flipping through the documentation to find it, but the particular command you do is to issue a command 0800 plus the new register window you want to port base IO plus 14, where the register window is between 0 and 7. And that will change the register window to some rwin prime. So if you're starting out and you're in register window 0 and you want to do a read, first you'd call this to change the register window to 1. Then you'd be allowed to call this. Do you have a question? Okay.
So that takes contribution.
Yes. Yes, and then it has to match. It'll be a type error. There's 2 things that you have to supply. One is the types of these operations, and the other is the actual code that invokes these operations, which makes up the driver. So it's this part is the specification. The driver code would be the implementation. And if the 2 don't match, the type checker will catch it. It's possible to get them both wrong. Right. that you can avoid. Oh, right, getting them both wrong. It happened to us once, yes. um, oh, sure. Right. Right. So yeah. So suppose, for example, you do an operation and then you have to go in and do a status check to make sure that the operation succeeded. And that status check gives you back some sort of integer tag value. 0 means okay, 1 means not okay. What would happen would be this would consume the capability and give you a capability that only allows you to go read the status register. Then the status register would give you back an integer tag value saying good or not good. If it's bad, well, let me start with the good case. If it's good, then it has this type. If it's bad, it'll have some type saying, oh, you know, there's some register window, but we don't know what it is. We don't know what the transmit size is. We don't know what the receive size is. We're back to square 0. Right. Right. So it'd be a much more elaborate version of the null pointer check that we had earlier. And of course, these types can get very long. The more complicated the specification you want to implement. All right. So a big problem is that in real life, not everything is a tree. Alias data structures like doubly linked lists and directed acyclic graphs are very useful, probably essential in practice. And we cannot store a linear resource in, say, this value here that has 2 different names for it. Because we could take the resource out using this pointer, and then somebody else could take the same linear resource out using this pointer, and there'd be 2 copies of the linear resource. So one way we can get around this is to add some limited support into the type system for allowing aliasing. And at Cornell, Carl Curry, Greg Morissette, Fred Smith, and David Walker have developed a couple systems for managing groups of capabilities where some capabilities in the group may be aliased, some may not. And there are a lot of complicated rules for how groups of capabilities are equivalent to each other or subtypes of each other and so on. We've taken a different approach. We found that this didn't quite get us where we wanted to be for implementing a garbage collector. So we pooled together groups of capabilities just using our ordinary data structure mechanisms. And it appears that we can actually encode these things using ordinary data structures, ordinary functions. We definitely know that we've been able to implement several garbage collectors using our technique here, which I'll describe. Before getting into that, let me point out really quickly something that Dan Grossman at the University of Washington noticed. And that's that it is possible to put in a linear resource inside a nonlinear data structure if the only thing you're allowed to do with it is swap. If I have a nonlinear resource saying I have a type T, which is linear in memory location I can take a linear value of type T and swap it with whatever exists in that memory location right now, and I haven't destroyed or copied any types. I've just moved 2 values around. So here's what I can do with this. I can store a tagged union, which says that in memory location 100, either there's nothing at all, or there's a capability for my Ethernet device. If I want to use this, I'll create another tagged union over to the side, which I know definitely contains nothing at all. And I'll swap it in with this guy. And then I'll check the tag value to see what I got. Did I get nothing? Well, maybe I'll try again and keep trying. Or did I get the Ethernet device? In that case, I'll go ahead and use it. So what I've got here is a simple spin lock. And rather than building it into the type system, it's something we can implement out of primitive operations like swap. Any questions about that? Now this is handy, but it's not something we'd really want to use to build a garbage collector. I don't want to acquire a lock every time I read or write through a heap pointer. So let me take an example here of a group of capabilities for addresses 3, 4, and 5. These are linear capabilities. They just say at those addresses we find a float in int and a bool. And let's consider two proof functions that manipulate these capabilities. Split just takes this pool of capabilities here, pulls out one memory resource, where in this case I is 4 and a is int, throws all the rest of the ones into some struct, and then we can merge the two back together. I'm going to claim that we can build a pointer out of this just by abstracting this a little bit here. Let's call the type of this pool P. And we're going to hold this abstract. I'm going to claim I don't know what the pool is. Let's call this junk here that we don't care about Z. The interesting operation is taking a linear resource that we do care about and extracting it from the pool using this split operation. And then when we're done with it, we'll use the merge operation to put it back. All right, this is horrible notationally. So let me just say that what I've written here, the type of the address is clear. We've used that before. This just says this pointer lives at some integer address I. These two are proof functions whose type just says what this diagram says. Split takes an argument P, returns a linear pair of type Z and the linear memory capability we're interested in. Merge takes type Z, the linear memory capability, turns them back into P. Earlier in the talk, I claimed that a pointer was something that contained an address and a capability. That's a little stronger than we need. Actually, a pointer can just be an address and something that tells us how to get the capability when we need it. And that's exactly what this is. We have an address I, and we have these functions that tell us whenever we feel like getting this capability for I, take the pool, pass it into this proof, and that'll give you this. And when you're done, use the merge function to turn this back into an ordinary pool. I claim that this is a pointer, and even better, it's non-linear. This is just an integer. It's not linear. These are just proof functions. They tell you how to manipulate linear resources, but they themselves don't contain the linear resources. I can make as many copies of this function as I want without having to worry about it. Okay, this pointer is horrible. It's polymorphic over 4 different things. The pool, the address I, the type of the data that lives there, A, and the type of this junk here that lives in Z. So I'm going to hide I and Z. And this type exists I and Z just means there's some I and Z in this pool pointer, and I don't care what they are. They're sort of private to the pointer. What I really care about is P and A. So using this pointer type, I can write a load operation that takes the current pool P and a nonlinear pointer into the pool and loads the value A. And all it's going to do is first read these 3 fields out of the pointer, and that's what this thing does here. Let the address split function and the merge function be the contents of the pointer. Call the split function to turn the pool into the memory resource we care about and some extra stuff Z. Do the actual load using the linear memory capability. Merge the linear memory capability back into the rest of the pool to form a pool, and return the original pool unchanged along with the value we loaded. At runtime, all of this stuff turns into a single load. The pool is just a capability itself. It's a group of capabilities, so it has no size. The pointer turns into a single address. This whole thing turns into an inline function that performs a load. But by using this, we can use linear memory types to encode nonlinear data structures. So for example, if I have a function g that points to a Boolean, and this pointer comes in variable p, I can make 2 copies of p. I'm sorry, if I have a function f that takes p, I can make 2 copies of p and pass them into g. And then g can take these 2 pointers, call this load function pload by using the pool in p1, using the pool in p2, and then do some operations on the Booleans that it loaded. In other words, this is exactly the example I showed using nonlinear capabilities near the beginning of the talk. Only now we've managed to encode it with linear capabilities. So we don't necessarily have to extend the type system with special support for aliasing capabilities. We can get it just with clever use of these proof functions, split and merge. I think it is. I haven't seen it anywhere else. Right, that was in alias types and yes, and capabilities, yeah.
It's really the abstraction that you're adding.
Right, right. In particular, a lot of the additional features of alias types, like special equivalence rules for groups of capabilities, subtyping rules for groups of capabilities, those are things that we can derive here rather than building into the type system. Okay, so I'm going to claim that we can build a garbage collector by using these pools. I'm not going to claim that I can explain the whole garbage collector in 5 minutes. So I'll just go through a very high-level overview. We can turn these pools into a mechanism for allocation by letting the type of the pool grow as you allocate data. So we have a mechanism in Clay where you can say, there are going to be some types, alpha 6, alpha 7, and alpha 8 yet, but I haven't decided what they are yet. Just leave these placeholders here. And as I allocate data, I'll define, okay, alpha 6 is now equal to int, and I want memory location 6 to have int, and alpha 7 is also equal to int. And I'll slowly grow the type, or I'll slowly refine the type of this pool as we allocate data. So this implements an abstraction called regions, where we can start to fill a pool with data. When we get tired of the pool, we've just got a collection of linear memory resources. Since they're linear, we can go change the types to whatever we want and deallocate the pool. When we do that, we may leave dangling pointers, nonlinear pointers into the pool. But that's okay, because the operations on the pointers, loading and storing, require the pool P that's associated with that pointer to work. If I destroy P, I will no longer have any meaningful operations that I can perform on a pointer that's associated with P. So dangling pointers are still safe. And about 5 years ago, Dan Wang and Andrew Appel at Princeton noticed that if you have regions, you can turn that into a copy and garbage collector just by saying, whenever a region fills up with data, allocate a new one and copy the live data to it, and then destroy the old one. And by destroying the old one in this case, we're just saying we're setting aside these linear memory capabilities to be used for something later. For example, maybe to be used for a third region. We can reuse the space over here to hold the data copied from R prime. So we use this idea to implement a simple copying collector with 2 semi-spaces where data gets copied back and forth from each one. Is this a good idea? So there's a paper I found really interesting. It's a PhD thesis from William Bevier from about 17 or 18 years ago. For his PhD thesis, he defined a small operating system kernel, about 600 lines of assembly language code, I think, which is probably, what, a couple hundred lines of C, maybe. And he proved that it was correct. I still find this very impressive. I also find it a little bit discouraging that it took an entire PhD thesis to do 600 lines of assembly language code. More properties about the program's reliability that you want to prove, probably exponentially more effort is required. As you will have noticed, we need a lot more type annotations to write a Clay program than an equivalent C or C++ program would. On the other hand, we get much stronger properties proved at compile time. So I wrote several garbage collectors with this. They always worked on the test cases the first time I ran them. Given the strong types, it was almost impossible for them not to. As part of her thesis, one of my students, Leah Whitty, wrote a driver for the 3C509 card. It only crashed once, and that was because the types that we specified were wrong. It was a specification error, and this is hard to deal with in any formal verification system. So we do get some gain out of this. We may be a little farther up this curve than I would like. And with that, I'll end the talk and take more questions.
So, second bit of what the garbage collectors and earlier development as well. Now, one of the big problems about the garbage collectors is doing the initial root set.
All right.
And I
We
think
have.
you ignore that completely.
Yes, we say that there's one root pointer, give it to us, and we'll start collecting. So let's see, what could we do about that? Most of the papers on typed garbage collection have assumed that the program that's using the typed garbage collector has been CPS converted and is allocating all of its frames on the heap instead of on the stack. And that therefore there's one root pointer just from the registers, which all point directly into the heap. We can probably do a little bit better than that, but we would have to specify pretty carefully what the layout of the stack frame is in terms of these types. Right now, we specify the layout of a heap object by saying things like the first word of the object contains a bunch of tag bits. The tag bits that are 0 correspond to integers. The tag bits that are 1 correspond to pointers. We would have to do something similar for stack frames. Yes? Oh, good. You have a question?
One of the things that on the recent slide we talked about how to get your non-linear type linear types, and one of the things you do is play around this pool. One of the things that seems to happen a lot in play is that after you've built the heinous thing with all the monotypes and fun, you eventually are able to abstract that away. Does that key ever disappear, or am I turning that key around with me forever, trying to talk about this is the pool I'm using, so that when the garbage collector gets called, it can take it away and give me back an email?
You are carrying that pool around, and it's very much like a region annotated program that says that for every function says for all regions row, take some objects that live in region row, and that row is always following you around whenever you need to talk about pointers that live in a region, maybe more than one row. So yeah. I wish we had fewer annotations. One of my students was working on generating some of this code automatically from a higher level language where you didn't have to have so many annotations. But then again, you didn't have as much power from that higher level language. I've seen two kind of practical ways of using regions. And this is essentially we've implemented regions, which is a technique that's been around um, uh, in the typed community at least 10 years. And one way to use regions is to build a garbage collected heap out of them. Before that, one way to use them was to try to analyze the program to determine lifetimes of objects and try to put objects into regions that could be deallocated directly without having to copy objects from one region to another. So if you have some sort of a region inference engine for your for a high-level source language, you could use this as a backend to type those. But those are the two main ways I know of using regions. Does that answer your question? The techniques I've seen, they don't always assume that the high-level source language is oblivious to regions, but that's a common assumption, that you'll write a high-level program in ML or Java or something, and then it's the job of the compiler to figure out where to put allocated objects in regions. Right, so we would use this to write the runtime system that does know about regions. And for most programs, rely on a high-level language compiler to generate the use of the regions. Yes?
How would you compare your work to other previous work in the stringless space for the second?
Okay. All right. All right, well, let me start with Cyclone. Cyclone and Clay have sort of been growing towards each other. So Cyclone has a more high-level language approach to memory where you can say malloc. Whereas in Clay, if you want to malloc an object, well, you would write your own allocator and write your own garbage collector. The only primitives Clay provides is load and store, which makes Clay much more difficult to program in for most high-level programming in Cyclone. Yes. Cyclone has at least yes, Cyclone has they have reference counting, they have regions, they've added, I hesitate to call them linear types, but they're at least affine, almost linear, as well as garbage collected types. So their approach has been to try to provide the programmer with a smorgasbord of useful memory management abstractions. And which ones you pick depends on your application. Our approach has been to strip everything down to load and store and capabilities allowing you to do load and store and say, build your way up from there. So as a result, if you wanted to implement an efficient, really low-level language that takes advantage of efficient heap layouts in something, it would be better to do that in Clay, assuming you want it to be well-typed. They have done a scheme garbage collector in Cyclone, but it wasn't as efficient as the ones we've had in terms of the heap layouts. Yes? Oh, we don't have exception handling because of the linear types. And
You're basically just giving up. We will not have exception.
yeah, I've thought about this a little bit, but it always seems to come down to if you did want to add exception handling, then you'd have to have all these additional kind of try finally clauses that say, oops, you're throwing an exception past a place where a linear resource is being manipulated. Please clean this up as the exception propagates for me. I haven't been able to think of anything better than that. And if anybody has any better ideas, I'd sure like to know.
It makes
Yeah.
sense. You can have an invited garbage collection that goes into you have a serious problem on your hands.
Oh, yeah. You know what? Here's an example of something that we don't catch at compile time in our garbage collector. What if you're copying a full heap into an empty heap, and the copied data actually ends up larger than the original data? That's not supposed to happen. You're supposed, when you copy data from one semi-space to another, you're supposed to be trying to compact it. When doing that copying, we overflow the end of the region, I don't know what to do. That's really not supposed to happen, but it's a property that's much too deep to prove with our type system. And we might want to do something like throw an exception that says this really wasn't supposed to happen, and it means there must be a bug in our program. At the moment, we just quit. And I wish I had a better answer to that. We can't prove everything statically as much as I would like to. Or maybe it's not a good idea anyway. The regions don't necessarily have to be fixed sized. We can certainly allocate, we can put together existing capabilities to form a new region of any size we want at runtime, just by moving capabilities from one data structure to another. So for instance, if we had two regions and we knew they were contiguous, we could break them up into their capabilities and put the capabilities together to form one big region.